exposure is from our observations, and put our observations with what we have learned, and we come up with those things. So right now we have this, and I want to relate what is a tau. And if let me pick a small cube here, just here. Okay, so that cube after deformations basically is like this. Okay, so that one I can draw is like this. That cube is here. And on the same cross section, and here I draw is a front side view. Okay, is a front side view, this cube, this one. And I draw is from the front side of the shaft. And then basically this line represent is this side. And this line represent is this side, okay, the whole side. So after deformations, this point will move to here. For example, this point will be moved to something like this. And for this one, we drawing is pretty much could be something here, okay. But here you can see this is this shape, including the distortion plus the rigid body translation. So if I cut off the rigid body translation, basically this one is equivalent to this one, right? And again, this is gamma. So really doesn't matter where we pick our cube. And basically the net change of the shape still can be quantified by this gamma, which is shear strength. Okay? Yes?
I know you said when it was a really small gamma. How small?
How small, yes. And from our examples last time in chapter 2, if you remember this example here, we have the P applied, and that is kind of the material. If you remember that material, that example, I think the gamma is 0.02. If my memory is right, radian. The 0.02 radian, which means 1/50. So that means 180 divided by 50, 3 degrees or even less. Okay. Okay, now for this case, now you can see in this case the tau will be happening on this side. Okay, so happening on this side or on this side. So basically what is tau? Shear stress happened to, again, this side represents this cross section, right? So tau actually represents is the stress on this surface. Okay? Okay, so now let me summarize here. So this is the one side of the shaft, and let me take a cut. So this is the radius C. And now for following these configurations, so now we learned that the tau is just like this direction. Here is so small. Let me get enlarged here. So this is our cube. So which means the shear stress basically is this tau. Okay, let me use the color. How about that? And for this case, the tau is circulation in this way, a T torsion, right? So we have a torsion, then induced the shear stress on one side. Basically, you should imagine this is a very, very small cube. We talk about is a localized information. So on this side, the tau is tangent to this point. The tau is tangent to this point and has the same circulation of the T. And what is tau? Tau equal to G times gamma. What is gamma? Gamma, let me pick up the information here. Here is, sorry. Let me just leave it. Okay, just leave it. Okay, let me write it out. C over L times V. Okay, and let me impose the phi. So this is a fiber. So for example, the fiber deformed to here. So for example, here is our phi, the angle of the twist. And once we have the loading applied, we'll get equilibrium. So that is the, so that is a twisting angle here. Okay, so once we get equilibrium, the angle should be fixed, should be a constant. And that constant should be corresponding to the magnitude of the torsion. If I twist it bigger, you can see that is twisted more, right? Okay, that information we got. One more time, I want to emphasize here we make assumption. That means once we, yes?
What does G stand for?
G is a rigidity modulus. And from our Hooke's law, that is G. And a call from heaven. What was the thing? I forgot what I'm going to say. Oh, assumption. Yes. This assumption is this. We assume that during this twisting, all the material points on the vertical, let me call this line is a vertical line, and all the points during the twisting will remain in the same cross section. What that means is this. So this is a cross section. This is a center, and this cross section can be taken from anywhere of the shaft. Okay. And for example, if this is the point before the loading applied, and once we apply the loading, all the material will be moving because the material response to the loading will deform. And deform, that means the material points within the model will going to move to the different places. Due to the loading, for example, if this is the torsion, reaction of the torsion in that section, then this point will remain on the same cross section here. That means this assumption simply exclude the possibility that this point will be moving out of the board. The displacement will happen only in plane. There's no, we call it warping or distorting. Okay? So that means if there's a point on this surface here, once I tilt it, the movement of that point won't jump out or jump into the different cross section. That is the assumption. I can tell you this assumption is very strong, and this assumption is not valid. The reason we can learn from, if you will have chance and to take ME 631, and I'm going to offer next semester, and I will give the reason. Actually, most of the deformation, the cross section will be distorted, which means originally the cross section is a plane, but once we tilt it, the cross section will become kind of they'll have a ripples. In particular, for this circular shaft, it's not as significant, but if I twist it, it's a rectangular shaft. And you could imagine rectangular shaft that will have we call it outer plane distortion. Okay, so this assumption is very strong, and make this assumption, to take this assumption will make all the analysis much easy. And by ignoring any outer plane deformation. Outer plane deformation will happen, but the matter is to how much. In the circular shaft, the outer plane distortion can be ignored, pretty much reasonable. But once we twist the rectangular shaft, then that distortion could be huge. Okay, can be compatibly huge. So now for this case, this point to here, then let me use the colors. So this represent is the final one. Okay. So based upon this assumption, we can make one step extension is this. If originally that is the diameter located onto the undeformed cross section, so after deformed, this diameter will simply rotate, become like this. So that means before deformation, one diameter is a diameter. After deformation, that diameter still to be the same diameter, but go to the different orientation. Yes?
Is there a condensed, because of the assumption, can we condense that into a saying so we can write that down? Is there an easy way to say the assumption in words?
Yes. This assumption is this. The diameter after torsion applied still remain in the same plane as the diameters. And I can let me make some counter examples.
Yeah.
So the counter example could be this. So this is the before deformed, that is the diameter, which means pass through the centers. The one counter example to violate this assumption is this. This point moved that much. This point moved that much, a little bit smaller than this one. So their connections won't be the diameter anymore because that won't come to the center. The other possibility is this. This is a cross section, and let me draw this is the outer plane. So here this is undeformed, and after deformed this point moves to here, but after deformed this point will move outer plane to here.
So it's
larger than this one. Not only have the in plane, but this one will also have the outer plane. This is the outer plane. This one's circular dash one represent is the outer plane, the information. Okay. So textbook has the very good wording. Let me see whether I have in my notes. When T is applied, AB and A prime, B prime remain as the diameter on the same cross section. Sorry, that's too low for people sitting in the back, but let me read it out for you. When T is applied, this assumption saying the AB, which is the diameter before deformed, and A prime, B prime, that is the deformed, corresponding deformed diameter, the both will remain as the diameters on the same cross section. On the same cross section, that is to preclude any outer plane distortion. And to remain at the same diameter to make sure they have the homogeneous movement around the circle, around the parameters. And so right now we have those things here summarized. And the next step is this. So let me write it up here. So far what we have is L gamma equal to C times phi. So right now we have done is on the information, along the parameters, because that is where we're coming from. We're coming from is here, I draw the patch. That patch is on the surface. And the patch associated is with the radius is C, right? And now I want to get the information inward. Before I move on, I want to ask, and say I want to move the into inward, for example, onto this circle. This circle is just like onion, that's the inner core. The circle has a radius, let me call the rho. Now I want to move the information into the inner layer. Let me ask you the one question. Would that be the same once we move the information back in, or it could be varying?
Well, the angle should be the same.
Angle will be the same. Twist angle will be the same, right? But the information, that is our next topic. Let me erase this one. So earlier, what we have done is this. We selected the patch. This patch is on the surface. Corresponding is the outermost radius. Okay. And now I want to switch. Say we pick up inner core of this row, just like this. So we can repeat the same process. But for this inner core, say if I take the free body diagrams on the inner core, can you imagine that would be this whole thing? I don't want to disrupt, but that can be shrunk, go down, right? So in this way, for following up, we go into the inner core information. The right away here, I simply change one parameter is this row, right?
Yeah.
Okay. So can you repeat the same drawing? For right now, I'm going to get information inward, okay? And this one represents, how about this? Let me draw one more time, so you can follow with me. So now I want to draw is a free body diagram of this inner part here. So let me draw that one here. A little bit smaller. And that would be the same size, the same length. And this is L. And for this case, this is rho. And rho is varying from 0 to C. So basically, rho is a parameter. Okay, depends on which layer we look into. Basically, this is more generic models. The same thing here on that free body diagrams, we can do the same, repeating the same information here. This is a patch. And then once deformed, this one becomes like this, etc. Okay. This will be another angle. So to make distinguish. And how about this? Let me make a label. This is I want to, because the two here. Let me finish this one. So this is the center. This is the twist angle. Twist angle on different. Doesn't matter which layer or which radius we look at, the twist angle will be the same. So for this case, I write the V like this. And here is the angle we're going to look for. And to make it distinguish, how about that? I add one more subscript here, gamma max. I'm going to explain why I put the subscript max here. But I just want to make the point is the two angles shouldn't be the same. They are different. Okay. So we put on this one. So for this case, the same thing. We focus on the arc length here to formulate. So in this way, you can see L times gamma equal to V times rho V. Will be okay? So in this way, you can see the gamma equal to L3 times rho. And here our parameters is this. Rho is a number between 0 and C, just like drawn here. Okay, we can pick any number of a row starting from the center, which is 0, to the outermost, which is C. So rho here is the parameters. So here we have these things. So therefore, you can see this angle will be minimum when rho equal to 0. This angle will be maximum when rho equal to C. That be okay?
Can you say that one more time, please?
Okay.